32 degrees outside, isn't it? 37. All right. So let's finish this problem that we started. And I think the furthest we got was part A, which was the easy part, find the equation of a line tangent. Did y'all finish this one? I can't remember what I said. I may have told you to do the other one. But I did put in the calendar to finish both of them, but I can't remember what I told you in class. Sometimes y'all listen to what I say in class. Whatever. Yeah. Doobie. Anyway. Okay. So let's finish this one now. We'll finish this and we'll go over the other one that maybe y'all did. So in part A, we did the tangent line at 0.91. We approximated the potato temperature at time 3. B, use the second derivative to determine whether this answer in part A is an overestimate or an underestimate. So what we used, what we did, we found a tangent, and we used the tangent to approximate function values. That gave you a huge hint by telling you to find the second derivative or to use the second derivative, right? Could you get the second derivative okay? You need to be able to do this. So my second derivative, and I can't erase my green circles up there, but my original derivative, my first derivative is negative 1/4 of h minus 27. I'm going to ignore the negative 1/4. Now I need to do the derivative of h minus 27. What is the derivative of h minus 27? Is it 1? When you open the windows, if the doors open, depending on which way the flow of air is. Could be. She's back. All right. When you are doing derivatives, pay very close attention, especially if it's not a typical problem, like a normal explicit function. We are differentiating with respect to t, and h is not a t. So we do the derivative normally. I'm okay with saying 1, but I'm not okay stopping there because we have to now multiply by dh dt, because anything that is not a t has to be given that implicit treatment. Are we good? Bad? Alex. Thank you. So I do that. There's my second derivative. Typically, they are not typically. I'll say sometimes they will tell you to find the second derivative in terms of h or in terms of t or something like that. I don't like leaving the dh dt in the derivative. So since I know what dh dt is equal to up here, I can now replace the whole dh dt with what it is equal to. And so I'm going to have a new second derivative, or a more cleaned up second derivative of this. So negative 1/4 of negative 1/4 is dh dt of h minus 27. I completely forgot there were warm-ups up there. I put them up there a long time ago. Did y'all get a warm-up? We good with second derivative? Now, how do we use that to determine if this is an overestimate or an underestimate? If you remember way back when we did these types of problems where we did tangent line approximations, yeah, if your function is concave up, your tangent line is below the curve, giving you an underestimate. If your function is concave down, your tangent's above the curve, giving you an overestimate. And so that's what we're trying to figure out here. And we're really interested in the concavity between the point of tangency, which is 0, and the estimation point, which was 3. So we need to know the concavity on that whole interval. And maybe it'll help to simplify this second derivative, because negative 1/4 times negative 1/4 is positive 1/16 of h minus 27. And now we are wondering, we have to determine if that will be a positive or a negative second derivative. What do you think? Do we know? The question, it's all about h minus 27, because 1/16 is obviously positive. Is h minus 27 going to be positive, or would it be negative, or will it change? People. What would make that positive? What would make that negative? I need some interaction here. H minus 27. Okay, it depends on the value of h. If h is less than 27, then h minus 27 would be negative. If h is more than 27, then h minus 27 is positive. So the question is, where is h? What can h possibly be? So we go back to the paragraph. H is the temperature of the potato, and they do say that the temperature of the potato is greater than 27. Right? So since h is greater than 27, that means my second derivative is positive. And if a second derivative is positive, that means we're concave up. Therefore, it's an underestimate. Because, and even though I've already said the second derivative is positive, this is probably good enough right here. Like I've found the second derivative, I established that it is a positive second derivative. I'm going to say again that dh, the second derivative, d squared h over dt squared is positive. And that would be your explanation. How do we feel? Okay. Part C is the tough part on this one. It's the separable equation, and these are very, very valuable. Although lately they've only been worth 4 points. That's still a lot. Like that's a lot of points for a single part of a free response question. But probably when this question was asked, it was 5 and maybe even 6 points. Who knows? I guess I could look it up. But anyway, so we have a new model for the temperature of the pizza potato. dg/dt is this thing, and they want you to find an expression for g of t. So that's telling you to solve the differential equation. Then plug in 3 to find the temperature of the potato at time 3. So we have to start by doing separation of variables for this differential equation. And do remember, on these problems, you need to be very meticulous and detailed in your work because there are typically a lot of points that they look for in each step. And the first point is separation. Can you separate that? You definitely need to multiply by dt, and then I need to move the g minus 27 to the 2/3 over. We'll do that by division. And I would leave the negative on the right side. If you want to divide by negative as well, you can. However, it's not needed. I'm going to leave the negative 1 over here, and then we'll do the antiderivative. Right side's easy. So negative t plus c. What about the left side? Can you do that one very quickly without doing any scratch work? Okay, if the answer to that is no, which it isn't for me, I would recommend going over here on scratch paper and solving the antiderivative separately. It gets really ugly if you try to do substitution or something like that inside the actual equation over here. So I'm going to come over here and isolate that ugly integral. And to do this antiderivative, it's not a natural log. My top is not the derivative of that whole bottom. So I'm going to bring the g minus 27 up, make it to the negative 2/3. And this one is going to be a quick one. Technically, it falls under the u sub category because we do have something ugly on the inside. However, the derivative of the interior is just 1, and when that is true, you can just treat it like it's x to the negative 2/3, and we can apply the power rule. So it's going to be the interior, negative 2/3 plus 1 is positive 1/3. Then we divide by 1/3, which is times 3, and that's your antiderivative. So come back over here, 3 times the quantity of g minus 27 to the 1/3. Now we need to solve for g and solve for c. Can you do that? What do you want to do first, g or c? Huh? Do I need to plug in 3 for t? Eventually. I'm not going to do that yet because plugging in t for 3 for t, is after you find the full equation for g. So we will eventually, but I'm going to use this condition right here. We know that when t is 0, the value of g should be 91. So I'm going to plug that in here. 3 times 91 minus 27 to the 1/3 is equal to -0 plus c. And this is non-calculator. What's 91 minus 27? 64. Now, how confident were you in that? Yeah. If it's a non-calculator problem, they typically give you numbers that work very well with the problem. They can give you something ugly, but I know the 1/3 power is the cube root, so I fully expect the interior to give me a perfect cube, something I can easily cube root, and 64 is perfect cube. Cube root of 64 is 4. So 3 times 4 is 12, and there's my value of c. So once I get c, I come back over here and I reset this equation, except I plug in the value of 4 for c. So 3 times g minus 27 to the 1/3 equals -t plus c. And it does say find an expression for g, so I'm still, that's supposed to be a 4. So I'm still going to, I need to solve for g. I will plug in 3, that's what I was going to say. I could go ahead and plug in 3 for t now, and I would get a value for g when t is 3, but I need to write the expression for g because they explicitly ask you for that. So g minus 27 to the 1/3. We're dividing by 3 here, so that'd be -t over 3, or -1/3 t. And are y'all paying attention? You know, like every other class would have been like all over me because they're trying to get my error count as high as possible. We'll let that count. Y'all speak up. Speak up. I had already divided by 3 in my head when I wrote the plus 12. So now it's a 4. Now it's 4. How do we undo the 1/3 power? Okay, we cube both sides, and then we add 27. So 27 plus this stuff cubed. That's ugly, wasn't it? Now we can finally plug in 3 because it does say find the temperature at time 3. So that's 27 plus -1/3 times 3 is -1 plus 4 cubed. Do you want to clean that up? You don't have to. That will get, as long as that's correct, that will give you correct full value, full points. However, I'm going to go against what I tell you. I'm actually going to simplify that. What does that turn into? 27 plus 27, which is 54, right? And the only reason I want to do that is because this problem, we've now answered 3 questions regarding the temperature of the potato, and I realized that part C was a different model. It's not the exact same model we used for A and B. However, in part A, we estimated the temperature of the potato to be 43 degrees. In part B, we established that 43 is an underestimate, so the temperature is actually above 43, right? In part C, we found the actual temperature, not an estimation. And so the reason I wanted to simplify is I wanted to see if my answer for part C was consistent with what we established in parts A and B. And I was expecting something in the ballpark of 43, because 43 was an estimate, except it should have been higher. Is 54 in the ballpark of 43 and higher? It's kind of a big ballpark, but it's there. I feel good about it. So I only did that just to give me a little bit of confidence in what I've already done. But now that I have that confidence, I'm going to scratch that out. That 54 was only for me. Why in the world would I scratch that out? I don't need it. I know that I can get full credit with 27 plus -1 plus 4 cubed. And if I messed up and I accidentally wrote 56, I don't know. If I accidentally miscalculated that while I was checking myself, it would have counted against me. So I crossed that out, and that tells the reader that they're not supposed to look at it, and they will grade this instead. So it may not be a bad idea to simplify your answers in some cases just to satisfy your own curiosity. If you choose to do that, though, cross it out. We don't read things that are crossed out. And then leave whatever was before. Good, bad, ugly? All right, now the one that y'all are supposed to do. Move this down some. A and B, I think were nice. A was a slope field, so let's see. So if I plug in 0, 2, that's going to be 4 over -1. That's a steep slope. Oh! You should have something kind of steep and negative, so I'll say -4 there. If I plug in 1, that's -1, or 1 over -1, that's a slope of -1. And then at 0, we have a slope of 0. And then over here at 2, it's a slope of 0. I think at 2, 1, it's a slope of +1. And at 2, 2, we're a slope of +4. So you should have had something kind of like that. 0's on the x-axis, and then gradually getting steeper as you work up. Cool. B, f of x is a solution to the differential equation with f of 2 equals 3. Write an equation for the line tangent. You're immediately thinking point and slope. The point given, 2, 3, the slope is from the differential equation. So my slope would be y squared over x minus 1. So 3 squared over 2 minus 1, that would be 9. So the tangent line would be y minus 3 equals 9, x minus 2. Are we good with that one? Then it says use this to approximate f of 2.1. So f of 2.1 would be approximately 9 times 2.1 minus 2 plus 3. And if you choose to clean that up, that is going to be 3.9. But again, I don't think we need that, so I'm just going to cross it out. Do the approximation, just satisfy curiosity, and then move on. Good? Bad? Those are nice 2 questions, aren't they? I like those. Number C. Find the solution to the differential equation. I'm going to need a lot more room than I have right here, so let me copy the differential equation. Y squared over x minus 1. And then let's scroll down and see what we can do here. So, find this solution. Can you separate it? The separation would be dy over y squared, and then 1 over x minus 1 dx. You okay with that? Now the antiderivatives. Which side's easier, left or right? So I usually like to knock out the easier one first. I think the right's easier, although the left should not be painfully difficult. The right side, the top, is the derivative of the bottom, so natural log of x minus 1. Left side, what about dy over y squared? Yeah, it's -1 over y. That's y to the -2. And the antiderivative would be y to the -1 over -1, which is the same as -1 over y. Cool. Do you want to solve for y or do you want to solve for x? Y? I'm not. I'm going to solve for x. Although I wonder if we solve for y first. It would be... Actually, I may go ahead and do this. Negative. It'd be 1 over y is negative natural log of x minus 1 plus a constant. And if you plugged in 2, 3, it actually... Oh, wait. We're solving for y, aren't we? If you wanted to solve for y here, you would just flip both sides. It'd be y equals 1 over negative natural log x minus 1 plus c. And the reason I didn't want to do that is because now I have to plug in the point 3, 2, and it's just a little bit uglier. It does work. Of course it works out. It works out. It's not that it's wrong. It's just we have a little bit more unpacking to do to solve for c, but not much. It actually ended up not being that bad now that I look at it. Because we have 3 equals, and natural log of 1 is 0, 1 over c. So c would equal 1/3, right? Or if I plugged in here, if I plugged in 3, 2, is it 3, 2 or 2, 3? I hit it. What did I plug in? 3, 2, 3. Okay, so I plug it in now. I have 1/3 equals negative natural log of 1 plus c. And this time I get c equals 1/3 again. Good. So it really doesn't matter what order you do it, as long as in the end, when you write your final solution, you have the same thing. So it's y equals 1 over negative natural log of x minus 1 plus 1/3. And I would leave it like that. That can be written in a little bit more aesthetically pleasing ways, but I just don't care. How's life? That one was a little bit nicer than the potato problem. Y'all feel that way? Yeah. Okay, and I completely forgot about the warm up. Y'all need time to work on that? Or do you need to go pick it up? So see what you can do with that, and we'll talk about some other stuff. So on that Continental Math League sheet, did y'all find it? Yeah. It looks like this. And it's got, 7 questions? And the answers to it are on my webpage. So if you want to go back and double check and do some more of them for practice, you can. So let's look at this one. So we have a differential equation, 2p, 1 minus p, and 2 minus p. And they give you 3 different initial conditions. And for each initial condition, what is the limit as t approaches infinity? My daughter, do you need help? Are you okay? Because it is on the back of there, isn't it, Linnea? Okay. Yeah, I was trying to save paper. I need to quit trying to save paper. The trees are overrated anyway. Nobody uses them in the real world. So we have this one, and they're asking you for the limit as t goes to infinity of the solution p of t, not of the differential equation. That's p, not dp. So one option, and you do possess the skills to do this. Don't write this down, by the way. One option would be to attempt to find the actual function p of t. And then if you find that function p of t, you could use the initial conditions to get the constants and actually apply the limit to those true solutions. However, we're going to run into a bit of a problem, because to get this solution in the separation, I would turn it into this. This is how I would separate it. I would leave the 2 on the right side and separate it like this. Okay? And then we would need to do the antiderivatives. And y'all should have the skills to do that. What kind of antiderivative am I looking at on the left side? A plane kind of problem? Oh, can't do a power rule. It could be y'all have listened to me too much and taken what I've said to heart to such an extreme level you don't know how to do that. Nobody? It would be partial fractions. You would have to do partial fraction decomposition to do that left side, right? But I did tell you we're not going to see that anymore, and you're free to forget it until you get to college. So if you have completely forgotten that, we're not going to do the partial fractions because it would just suck. We're just like, there's an easier way. And the easier way is kind of an out-of-the-box type of thinking. We're actually going to sketch a very rudimentary slope field for this one and think about what the slope field is telling us. Now, first, pay attention to variables here. P is the same as a y. It's dp dt. So my vertical axis is P, my horizontal axis is T, and what I'm noticing, and if I'm sketching slope fields, the easiest slope to identify and work with is the zero slopes. So the first thing I'm going to do is think, when does this give me a zero slope? Well, when P is 0, when P is 1, or when P is 2. Just remember that's on the vertical axis. So P is 0. I'm going to have 0 slopes anytime P is 0, all the way across. Right? When P is 1, we're going to have 0 slopes anytime P is 1. And when P is 2, we're going to have 0 slopes anytime P is 2. Good? Then I'm thinking, if those are the only places where the slope is 0, let's think about positive slopes and negative slopes. What do you think is happening between 0 and 1? Well, we could pick a test point. What's the number between 0 and 1? 1/2. What if I plug in 1/2 here? 2 times 1/2 is a positive. 1 minus a half is positive. 2 minus a half is positive, right? And so that means everywhere between 0 and 1, we have positive slopes. So I'm just going to draw a bunch of positive slopes. Are we good? And I know the rows are the same because it's only a function of p. It's like that trick. If your differential equation is a function of y, your rows are the same. Function of x, the columns are the same. So p is like my y. So I know I'm going to be the same all the way across once I establish a single slope. Between 1 and 2, if I plug in a number between 1 and 2, I have a positive. 1 minus something larger than 1 is going to be negative. 2 minus something below 2 would be positive. Those are all negative slopes. Yeah. And then if I plug in something north of 2, if I plug in a really large number, I have a positive times a negative times a negative, which gives me positive slopes. So we have a rudimentary slope field here, and I can sketch the solutions with each of these initial conditions. My first one is starting at 0, 1/2. Where is that going to go? It's going to start by going up, but we have that equilibrium solution which acts like a horizontal asymptote. So we're going to go up, but we're going to level off like that. So what's happening to that solution as t goes to infinity? It's approaching a value of 1. Yeah. What about 3/2? That's 1.5. That one's going to start with a negative slope, but again, it's going to approach that equilibrium solution. Also going to be 1. And then for c, 5/2 is up here. Where is it going to go? It's going to go up, and there is no horizontal asymptote up there. The only 0 slopes were at 0, 1, and 2, so that's going to go up forever towards infinity. That was a weird problem, wasn't it? Looking for those equilibrium solutions. Yeah, maybe. I don't want to do every problem on here. What do I want to do? 1, 4, 5, and 7. I really like 4. I really like 4. And 5 and 7. So I'm going to give you a few minutes. I want you to see what you can do with these 3. Actually, I'll do them all on these pages. 1, 4, 5, and 7. And they are all multiple choice. Does that make it easier? I think so. So let's see what you can do with these. Okay, by now we should at least have a game plan. Have we done anything on 4 yet? Maybe. I would replace the f prime with dy dx, and you're solving, you're finding the solution, the graphical relationship between the two. You figure that out by looking at the equation of the graph, and basically it's asking what does this graph produce. All right. So see if you can solve that differential equation. And then we'll look at it and see if we remember what each of these look like. Yeah, sometimes I forget to freeze screen. Okay, so here's how far I got. I stopped here. It's a very quick separation and integration. The thing is, can you interpret that? That's an equal sign. That looks like plus. Can you eliminate anything? There's 2 I can eliminate right now. I can eliminate a line because a line would be y equals mx plus b. You don't square your x's and y's for a line. And why are you eliminating hyperbola? Which we can. I'm just wondering. Okay. There's Yeah. Uh, the next one I would first the next one I would eliminate is a parabola, because a parabola you have one square term. It's like y equals x squared or x equals y squared. You don't have y squared and x squared. So I'm definitely eliminating a and e. Now circles, ellipses, and hyperbolas do have x squared and y squared, right? Um, and generally you write them with x's and y's on the same side of the equation. So I'm going to do that. So I'm going to move my x squared over. X squared over 2 plus y squared over 2 is equal to c. And I can eliminate a hyperbola. For, I think, Alex, were you saying this? For hyperbola, it's x squared over something minus y squared over something. Well, it could be the same thing, actually. Y squared over something equals 1, right? But you want to be subtracting your squareds for hyperbola. We're not, we're adding them. So now it's down to circle and ellipse. What do you think? It is circle. Now, now I did change the wording on the question. If you look at yours, your wording is slightly different than what I have. I went through and I edited it and changed the PDF, but it was after I made copies of it. Yours simply says like can be described or something like that, right? This one I would go with circle, because a circle is x minus h squared plus y minus k squared equals your radius squared. That's your circle. And if you multiply this equation by 2, you would have x squared plus y squared equals technically 2c, right? So I like circle. However, the original question was poorly worded because an ellipse, or because a circle is an ellipse. It's like the whole square is a rectangle thing. So that's why I went in there and I said can most accurately be described, because a circle is a little bit more descriptive than simply calling it an ellipse. For an ellipse, you would want the numbers under x and y to be different. That's what makes it longer in one direction, forcing it into an oval. Good. Yay. How do you do on this one? Did you? Oh, you're not done. Y'all can't do these in like 5 seconds. Huh. Um, Separation, divide by y squared, multiply by dx. If this were free response, that'd be worth a point. So do that, even if you can't go any further. For the antiderivatives, I have done over the last week. I've done the antiderivative of 1 over y squared so many times. I've gotten it memorized. It's negative 1 over y. You can march through the power rule and clean it up if you need to. So the antiderivatives were nice, and I went ahead and solved for c at this point. The only time, I shouldn't say, typically the only time I solve for y first is if that y is inside a natural log. Usually in those cases, it's easier to solve for y first, in my opinion. Otherwise, I'll solve for c, which I did. I got negative 3 for c, and then I plugged that back in, and I got that. And then guess what I did? I went ahead and plugged in 2. I don't need the full equation as a function of x. You can. I'm not talking about extreme levels of difficulty in solving that. However, I went ahead and I just solved. I plugged in 2 for my x, and then I solved for y. Cool. Cool. All right. So for homework, you've got like 6 days to do this, I think. On that same sheet are these free response questions. Do the 1998 problem at the bottom. They allowed graphing calculators on that one. However, the graphing calculator in 1998 could not do antiderivatives. So try not to take advantage of that feature. Really, you only need it for like the scientific calculator part of it. But anyway, see what you can do. Yes, it was. Y'all have a great weekend.